Can you guys see my screen?
Yeah.
All right, good. Okay, so waves. Uh, have you all of you have you covered this in like school or in your college?
Mm.
Yeah.
No.
Yeah.
Okay. Okay. Good. Okay. So yeah, waves. Uh, yeah, basic definition of that would be wave is something that actually carry the energy from one place to the other while not carrying the material like matter uh, along with it. So at the end of at the end when the wave has passed through, the matter or the material just stays there. It's just the energy that is transferred. So it's one way of transferring energy. So it's through waves. Um, so I'm just going to go through the important things which are absolutely necessary for the exam, not just going to like go through each and every word that the textbook or the revision guide says. Um, if you think that I've missed something or you think that I'm going very quickly, just let me know. So whenever you see a graph that shows wave, uh, there are two types of that. So one of them which is shown here is displacement versus distance graph, in which you basically have like different points in like if you just throw like a uh, stone in a pond, you'll see that waves are like moving. They just start from the point where the stone hits the water. So it's basically distance versus displacement graph that you are seeing over there. So basically that is that. And there's another way of showing wave using a graph, which is displacement versus time, like this one, as you see here. So both can be used in different ways. I'll just go through the one that's the most important, and usually you'll see this one mostly. So this is displacement versus distance. So what are the different characteristics or quantifiable things that we can actually like calculate or actually quantify the wave in? So those are displacement, amplitude, and wavelength. So displacement is basically at so in terms of displacement versus distance graph, displacement is basically the so from the mean position would be an undisturbed position, so that would be like zero position here. So how much is like the material or the matter, like for the example of a ripple tank, how much the water has moved up or down from its mean position. So at any point, that would be called displacement. So if I take any point, for example, like this one, so whatever is its distance from the mean position would be displacement. The maximum uh, distance or the maximum distance it travels from the mean position is called amplitude. And yeah, so this is amplitude. Displacement could be equal to amplitude when the material has moved its maximum position from the mean. Uh, and amplitude is just that maximum position, that maximum distance from mean. Wavelength is from crust to crust. Crust is basically the uh, positive extreme of a wave, and trough is the negative extreme of the wave. So from a crust to crust or any particular point on wave, and then the next similar point on the other wave in displacement versus distance graph. So it could be measured from this to this where it is shown in the book. It can also be measured from a very random position like this one and up till the other point, which is this. So that will also give you the same distance, which is wavelength. The other things that we can measure using that is period. Now, period is uh, how much time. So for period, it is mostly more relevant to look at the other graph. So if you look at displacement versus time graph, uh, it would be the difference between displacement versus time graph is that if you just take one point in a ripple tank, just a single point, and you see with time if it goes up, down, and you just plot it, how the displacement changes with time, then you'll get this type of graph. So time period is basically you start from any random point again, and how much time it takes for the wave to get back to the similar position. Like, and it should be moving in the same direction as well. Like, for example, if I take this point, obviously this point also has the same displacement, but it's moving downward. Like when the time moves forward, obviously it will be going down. So that's not the similar position. The similar position would be this point plus this. So that is, so total time taken for that is known as time period or period. Um, Frequency is just the inverse of that. And in words, if you have to say, frequency is just how much of a wave has passed through a single point in like a second. So and we measure it using hertz. Phase is basically a way of quantifying the position of displacement at that point. So you can obviously measure the displacement like that, so it's fine. But displacement you cannot like actually uh, distinguish between this point when the wave is going up and this point when the wave is going down. So to distinguish between that, we use phase. So uh, we can go into more detail about phase later, how it is measured. The phase difference is uh, phase difference is mostly we have the phase difference measured when we have more than one wave, and we say and we want to measure how much one wave is lagging behind the other. So we actually calculate the phase for one, then for the second one, and then we just take the difference of that, and that is phase difference. So I think this is pretty much standard. So I've already told you the relation between frequency and period. So they are inverse of each other. This formula is very important. This is V is equal to F lambda. It's universal formula. Uh, yeah, it's straightforward as well. V is actually the speed of light, of F is frequency, and lambda is wavelength. So they are related, yeah, using this equation. It's also called wave equation. It's very important. Moving forward quickly. So as I told you, uh, you can show a wave using two types of graphs. One is displacement versus distance, and the other one is displacement versus time. Normally, we use displacement versus distance graph. This is what we use. But using this graph, you cannot actually calculate frequency. You can okay, you can calculate frequency using the wave equation, but not directly from the graph. For that, you would need displacement versus time graph. So, okay, there are two types of waves. One is transverse. Is it clear till this point? I think it's really straightforward. It's not rocket science so far. Has anyone any problem? No? Okay. So, yeah, so there are two types of waves. One is transverse wave, and the other one is longitudinal wave. So the difference between the two is in transverse wave, the vibration or the movement of the material is at right angle to the direction of travel. Like for example, in the case of a ripple tank, or in case of disturbance in water. So obviously the uh, movement of the matter or the vibration, it is at 90 degrees to the direction of the travel of the wave. By the What they mean by direction of travel is also that the energy, it is moving to like at 90 degrees to the vibration. So yeah, so basically whenever they are at right angle, that is called transverse wave. Um and opposite to that is longitudinal wave. In longitudinal wave, uh, the movement of matter or the vibration is also in the same direction as the direction of travel of the wave or the direction of travel of energy. So that's the difference. Intensity is another. thing that can be measured to quantify a wave. So intensity is just the measure of energy per. So basically, it's power, uh, like how much power is concentrated in a unit area. So that's why the formula is unit intensity is equal to power over area. Uh, so yeah, it's also pretty straightforward. What else you need to know is that intensity is directly proportional to the amplitude squared. This will be very helpful in some of the problems related to this topic. Does that make sense? Okay, good. Okay, so yeah, we went through two types of waves, transverse and longitudinal. Uh, um, there are waves called EM waves. So this is like you can say a subtype of transverse or longitudinal. Basically, these are also uh, transverse waves. So this is just one subtype you can say of transverse wave. EM waves or electromagnetic waves, they basically have uh, two types of waves combined together. One is the uh, electric wave and electric field, and the other one is the magnetic field wave, and both of them are at 90 degrees to each other when they travel. But the vibration again is at 90 degrees to the direction of the travel of the wave or the direction of travel of energy. Uh, and with waves, there comes other properties that can be measured or that phenomena that can be seen. Some of them are listed here. So reflection, diffraction, interference. These are some of the phenomena that are related to waves. So again, they show uh, that the EM waves can have different wavelengths. They based on their wavelengths, they are divided into different like subsets. So as per the wavelength, so you can see that radio waves are one of the longest EM waves, and gamma rays are the shortest wavelength EM waves. Obviously, we utilize and they have some application based on the wavelength of them. So maybe it will come later on when we go through it. So one of the properties or the phenomena that is related to waves is polarization. So polarization of wave is, so if it's a just a random wave, it could have multiple like orientations, or it could be at an angle uh, related to some reference plane. So polarization of waves means that we actually eliminate all the other uh, all the other parts of the wave and just keep it into like a single plane. So basically polarization is when we want to have just the oscillation in one direction, and just eliminate all the other directions of wave that were the part of it. So it just gets rid of them. It is very useful in some of the applications related to biomedical imaging, where they actually use this, and because of that can see some parts of their sample which are not possible if the wave is not polarized. Okay, so and then they talk about how you, if you can just do this experiment and see that how when it passes through the vertical fence, a rope, then you can just see the vertical wave passing through it, not the other part of that. Um, then then they just talk about this. They have like two polarizing filters. Both of them are identical to each other. If they have like vertical stripes, and if you put the other one that also has vertical stripes, you will see that only the vertical waves pass through it. If you give it some unpolarized light, which has like uh, which has like uh, which has parts of it in different directions, so when it passes through it, it will just have like a vertical uh, vertical wave going through. But if you try start to rotate the other one, what happens is that from the first one only the vertical uh, wave pass, and the other all of them are like obstructed. But when you are going through and you're rotating it, it's not fully horizontal. It's still between vertical and horizontal. So what happens is some of the light can still go through. Why? Because when it is at an angle, you can always split it into its vertical and horizontal component, right? If you have studied vectors and you know that this is something that the lines, they are basically not vertical or not horizontal, they have some angle with the horizontal, you can always split it into its horizontal component and its vertical component. And whatever is the vertical component of it, whatever is the weightage of the vertical component out of one, basically that much of the vertical uh, light that is coming from the first polarization filter would pass through the second one. Does that make sense? All right. Um, I'll just take it as you are understanding everything. Okay. Um, polarization of waves. They are again talking about it. So they say that for longer, uh, when you have a like when you have like radio waves, because they have very long wavelength, you can't witness polarization if you have very thin lines, or when the distance between the lines is very short, you can't really see polarization. To polarize bigger wavelength waves, you would need to have like bigger split into, or bigger distance between the those vertical lines through which the waves can pass. So that is what they talk about, and I don't think there is anything else that is necessary here. The other phenomena is diffraction and reflection. So this is also something that is only related to waves. So when we are studying light, so sometimes we say that light behaves like a wave, and sometimes we say that light behaves like a particle. So we have to like prove how it behaves like a wave and how it behaves like a particle. So when we say that it behaves like a wave, we have to prove that light does all of these things that are written here. Like you can polarize light, that tells us that it's a wave. Light can diffract, light can reflect, which also tells us that it's a wave. So only waves can do this. So that's why we say that light has a wave-like nature. But also light has photons. Light has small packets of energy. Light can hit an electron and like uh, make it lose its orbit around the nucleus. So that is something that only a particle can do. So light has dual nature. So we prove it using these quantities. So diffraction and reflection. Diffraction is when light, when it passes through a small slit, or when it passes around a corner, it basically expands. So that is called diffraction, and that is a wave property. Uh, they have shown a ripple tank, and they are trying to demonstrate uh, how diffraction works. So when the gap is big, obviously the diffraction will be unnoticeable. It will be still there because light is still passing through the corner here. Obviously, it's not like light will go straight. You will see that after going through some distance, light has actually started to expand. So, but it's not that noticeable when the gap is a lot bigger. When the gap is smaller, it's a small slit. You'll see that light is diffracting from there, and when it becomes so small, you'll see that it actually has a significant effect of on the diffraction of the wave. So yeah, that's about it here. And also, if you see here, if you have like like an obstruction in the path of like any wave, you'll see that it has a shadow at the end, but it's not like it just stays like the width of the obstruction. It somehow just becomes like a, because of diffraction, it becomes like, you can see it becomes pointy at the end. So the shadow will be just through this part, and you see light on all the other parts. So yep. and they extend the diffraction from here. So this is a common slit experiment that is done with light. So the light here is collimated. Collimated means that the light here is just going straight. It's not expanding. It's not focusing. But as soon as it passes through the slit, it starts to expand, and which is actually diffraction. But when it does that, you'll see that it has some patterns here. So it's not like the whole screen is as like you can't see the light on the whole screen. There are dark lines, and there are some spots where there is bright light. So do you guys know why that is? Why does that happen? I know this is diffraction, but why does that happen? Do you guys know? Any of you? No? All right. Okay. So obviously it looks like that it's just a single wave that passes through it, but obviously there are a lot of small waves that pass through this small slit. So what happens is all of them expand in like all of them expand unrelated to each other, and when they do that, uh, there is some interference. Do you guys know what interference is?
Yeah.
Yeah, so because of interference, where there is constructive interference, you see bright light, and when there is destructive interference, you see dark fringes. So we will go through more. I think it's upcoming. But you should know that this is the slit experiment. It's not the double slit experiment, but it's almost the same thing in a way that there is not a single wave going through it, but also multiple waves that are passing through it, and because of that, we see these fringes. So yeah, that's diffraction. Um, Reflection, I think you already know. So for reflection, you just need to know that incoming light uh, hits a reflective surface, and it just gets reflected back, and the angle of incidence and the angle of reflection are equal to each other. And what is the angle of incidence? It is the angle between the incoming light uh, and uh, the axis that is normal to the reflective surface. So this is normal. The angle between incoming wave and that is the incident angle, and the reflected would be between reflected wave and the normal. So that's pretty much it in terms of reflection. Uh, Refraction and refractive index. Refraction is when light passes from one medium to another medium. It does not stay in air. It either goes from air to water, or it goes from air to glass, or it moves from uh, dense air to air that is not dense, or it goes from warm air to colder air, because there will be a slight difference in the refraction of all of them. So whenever light travels from one travels from one medium to the other, then you can witness refraction, which is the change of its path. So if it's going like this, like straight, obviously when it passes through something, it goes to another medium, it will have some consequences. It will have like change or shift in its path, depending on what angle it is making normal to the boundary of the medium. So if you see this, the light is so outline of a block. It's some block, we'll just consider it a glass or something, or it can be any other medium that is there. So you can see that there's an angle of incidence, then there's an angle of refraction inside, along the normal, and then again there's an angle of incidence and there's an angle of refraction. Okay, so you have to I don't know if it is very important to remember this, but just to justify yourself, uh, when light goes from uh, like a less dense uh, medium to a more dense medium, the angle of refraction is less than the angle of incidence. When the light goes from more dense medium to less dense medium, the angle of refraction is greater than the angle of incidence. And why is that? I should have opened a. Let me just open. to- Yeah. So just to explain it to you, so this is a boundary. My drawing is not that good. This is a boundary, and obviously, the normal would be like this. And let's say the refractive index. Refractive index is a property of that medium which tells us how quick the light will go through it. So if it's optically dense material, light will travel slower in that material compared to an optically less dense material. Like air has a refractive index of 1.000 something, and water has around 1.3 something refractive index. So this is an optically denser material, which tells me the light will travel slower in water as compared to light when it travels in the air. So if that is the case, let's say I have a wave that is traveling like this. So this is these are called wave fronts. So so okay, you see that this point. Let me draw it like that. You see this point hits the other bound, like hits the boundary and goes into the medium first, then this one, right? So what happens is uh, this goes first, and I told you that the light travels slower in a denser material. So what happens is that this now becomes slower. The part that goes inside becomes slower than the part that's outside. What it does is it creates a tilt. So when this light goes in, when it passes in, uh, okay, happening again. So when it passes there, it will kind of start to make this kind of pattern. So basically, it tilts itself because this point it enters the other medium, the optical dense medium first. So there's a tilt in that, and because there's a tilt, uh, it just moves like this. So if you think about it, this is normal, and this was the angle of incidence, and because it tilts like that, uh, this angle becomes smaller than this one. So angle of incidence is greater than angle of refraction because this part enters the next medium first, and it becomes slower than this part. So this goes faster, and because of that there's a tilt, and that's why the angle of reflection would be less than the angle of incidence, and it will be opposite to this if light goes from uh, denser material to less dense material, because when light enters into the less dense material it will now start to move faster, and because of that there will be an increase in the angle of reflection. Does that make sense? All right. Okay. Okay. So yeah, so that is refraction. That is it. And the value of refraction, it's basically just a ratio. I told you that refractive index, it's the property of the wave which tells us how quick the light goes through it. And we say that when the light goes slower through some material, we say that it has less. It's optically dense material, and when the light goes faster through something, we say that it is less optically dense. So refractive index is that, and that's why the formula of refractive index is n equals c over v. Basically, we are comparing the velocity of light through that material. Uh, yeah, we are comparing it to the velocity of or speed of light in vacuum. So c is the speed of light in vacuum, and v is the speed of light in that material. So that's why refractive index is equal to c over v, and it is always greater than 1, because there's no light can never go faster than when it goes through vacuum. So that's why it's always greater than 1. In vacuum, the refractive index would be equal to 1. In air, it's not exactly equal to 1. It is 1.0003 something. So it is more than, but I think in your case it would just be equal to 1 when you have to do some calculations. Does that make sense? All right. All right. All right. Snell's law. So Snell's law is again uh, something that quantifies uh, refraction. So it is related to refraction. Snell's law just says that uh, if light goes from one medium to the other, the product of its refractive index times sine theta, theta is the angle that it makes with the normal when it is in that medium, would always remain constant. That's why n1 sine theta 1 equals n2 sine theta 2 means that this uh, angle that it makes with normal when it is in one medium, uh, uh, if you take sine of that and times it by the refractive index that is there, it should be equal to the similar quantity inside when the angle is theta 2, which is the angle of refraction. You take sine of that times the refractive index of that material. So it's just that. So simply Snell's law is just this formula. That's it. Um, and based on Snell's formula, we can calculate the critical angle. So do you guys know what critical angle is? Anybody knows what critical angle is? No? Okay. All right. Okay. So critical angle is basically okay. So as I told you that when light goes from so I told you the other way. So yeah, let me just go back to this. So when light goes from now let's say this is my this is air, so refractive index would be equal to 1. This is water, so refractive index would be equal to 1.33 something. So when the light is traveling from water to air, what will happen? Because this is optically dense material, the angle of refraction would always be the angle of refraction would it be less than or would it be greater than the angle of incidence? So what would it be? You guys know?
The angle of refraction will be more.
Yeah. So the angle of refraction would be more because obviously it's going in a uh, faster medium. So so if you keep on increasing the angle of incidence, the angle of refraction would obviously be will keep on increasing. But there will come a point when the angle of reflection would just be that the wave the light wave does not even goes to the other medium, it just remains over the boundary. And that angle of incidence is called the critical angle because you keep on increasing the incident angle, and obviously the angle of refraction is greater than that. There will come a point when the angle of incidence is below 90-degree, but angle of refraction becomes 90-degree. So that incident angle is called critical angle. Critical angle. So if I have turned off. Just give me 1 second. Yeah. So there will come a point when the angle of incident would be equal to such a value that angle of reflection would be just equal to 90 degree, and that angle of incident is called uh, critical angle. You don't need to memorize this equation. This is just Snell's law, nothing else. So you just put the values. When theta 2 is equal to 90 degree, will be equal to 1. And when you are taking the water and you're basically taking water and air. So air has a refractive index equal to 1. So this equation becomes Snell's law just becomes sine C equals 1 over n. That's it. Yeah. So, and if you increase the incident angle more than the critical angle, then the light will never go to the other medium. It will just reflect, and you will follow the rules that are for reflection, that incident angle will be equal to the angle of reflection. So yeah, that's pretty much it. Then we have superposition and coherence. So superposition. So what is superposition? So superposition is when there are two waves, they are traveling, they just pass each other, or at some instant they are at the same position. It could be that they are traveling in the same direction, or they are at some angle, or it could be anything, but they pass through the same point. They have to, so there's a phenomena that happens there which is called superposition, when there are or two waves, or more than two waves could also be at one position. So that is called superposition. Now what happens in superposition is interference, which we will talk later. So here it says superposition happens when two or more waves pass through each other. So that's it. So if you see this figure, when they pass through each other, the first one, you can see that its amplitude increases because they add up, and this is constructive interference. And when they have passed through each other and moving in the other directions, you'll see that they again have the same amplitude that they had before. uh, Similarly, they can be destructive interference as well, which is shown here. So when they are at the same position, when superposition happens, there's no wave at all because their amplitude is equal but in opposite direction. So they just cancel each other. The displacement is equal but in opposite direction, so they just cancel each other, and that's why you just see a flat line and no wave at all. So you already know what is constructive or destructive interference. When crust and crust are at the same position, there's a bigger crust because it adds up. When there's a trough and trough meet each other, that's also the same case. There's constructive interference. But when a crust meets a trough, or yeah, so that is destructive interference. As long as it is destructive interference and you may not see a flat line, it depends if both have the same amplitude. If the amplitude is not the same, then you still see some light at the end. It's not like light or whatever wave that we are talking about. I just take an example of light. So you'll just see something, as long as there is a destructive interference and the amplitude of both of them is the same, then you'll see a resultant zero wave. There's nothing at all. Uh, we talked about phase. So if you have to measure phase of any wave, so you take displacement versus distance graph. So it's basically just to point out the positions. As I told you, this position looks similar to this one, but here the wave is moving downward, while here the wave is moving upward. So this position is exactly the same as this one and not this one. So just to distinguish between the two, we we say what point is in phase and what is not. So this point and this point are not in phase with each other. This point and this point are in phase with each other. Now you measure phase in angle, so it's an angle we use. You can think of sine theta. So sine theta is basically what you can apply. So you know that, just think of it as a sine theta graph. Have you seen a sine graph? Do you know what a sine graph looks like? Does it look like this? So it's basically sine graph, right? So here, when it starts, it's sine 0 degree is equal to 0. That's why displacement is 0. So this is 0 degrees. At the top, it has the maximum value, the amplitude. So we say the phase here is 90 degree because sine 90 is 1. So it keeps on going like that. So this is 90, phase here is 90. Then here it is 180 because sine 180 is uh, 0 again. This is 270 and this is 360, and it keeps on going. So every 2 pi, it just repeats itself. So whatever the value is here, if you add 2 pi to it, it will go to this value, and basically these 2 points are in phase. So every 2 pi, the points are in phase. And what points are exactly out of phase? So every pi. Do you know the difference? Like, there are different ways to tell the angle. One is in degrees and one is in radians. So all of you guys know about that?
Yeah.
Yeah, so 90 is pi by 2, and 180 is just pi. So yeah, so usually we represent this in radians. So this pi, it's basically in radians. So yeah, so I think it's pretty straightforward. When you have to measure phase difference, it is usually between two different waves, and we see where the other wave is with respect to the other one. So we subtract the difference between the two just to know if they are, like, the crust aligns completely with the crust of the other. Then we say that the phase difference is 0, because whatever the value of that wave is at a single point, the other wave will also have the same value for phase. So the difference would be just 0, and there will be constructive interference in the two. Okay. To get interference patterns, the two sources must be coherent. So two sources are coherent if they have same wavelength and frequency and fixed phase difference. So their phase difference does not change. So they are coherent waves. So coherent waves are basically exactly the same waves, and if the waves are exactly the same, that means they have the same wavelength. And if they have the same wavelength, v is equal to f lambda, they should have the same frequency. So if as long as they are in the same medium. So I don't know why they had to say both of them separately, but if two waves have the same wavelength and are in the same medium, uh, they they would be coherent, because their phase difference will always be fixed if they are moving in the same direction. So yeah, so pretty much it. So those waves are no called coherent waves because they are just alike. There's no
Sorry, I've
difference.
got a question.
Yeah.
But for phase difference,
hmm
if you've got how do you answer the question that says what happens to like point B, for example, as the wave progresses?
What happens to point B as wave progresses is what
Yeah,
you're asking.
like how do you answer that?
Yeah. So this is a displacement versus position graph, right? So in this case, uh, this point will just move down as the time progresses. So its phase value will change. So at this point, whatever its value is, it will keep on adding to it. So uh, this will actually move down as the time passes by. So you will say the phase, how much the phase changes will depend on the frequency. So if the frequency is given, you can calculate how much the position changes for B. So basically, it will just move up and down. And because of that up and down movement, obviously, wave is passing like that, but the point B is just moving up and down. It's basically its phase will keep on its phase will keep on changing with time. So whatever is the value, let's say at A, for example, if it is in the middle, I think it's 135 degrees, whatever it is in radians. So as the time passes by, its its phase will keep on changing. So its phase will change from 0 to 2 pi. It does not matter if it goes above 2 pi, as long as you mention 0 to 2 pi, whatever the value is for that. As for example, if point A comes to like this position that its displacement is 0, you can say that it is equal to pi in that case. So its phase value will keep on changing in that regard. Does that answer your question?
Yeah.
Right. Okay. Yeah. So this will make it more clear. So path difference is one other thing that you should keep in mind. So path difference between two waves. So the waves are now coherent, is what they said to us. There must be a path difference between them. Path difference is, let's say, one wave started from okay, let's say one wave started from here and the other wave started from here. Let's say they are they're completely identical, but they started from some other points. So the path difference would be this length, right? And you would measure this path difference in terms of the wavelength. How many, like not in wavelengths, like you will measure it in wavelength. Like let's say in this one, I have not made it very clear, but let's say the difference is there are two wavelengths ahead. The one of them is two wavelengths ahead of the other one. So the difference between them would be double the wavelength. So if you look at this formula, the path difference is for the path difference for a constructive interference is n lambda. So if it's a multiple of lambda, it's a multiple of wavelength, it tells us that both of them will be in phase every time. So uh, where is it? Yeah. So I have not made them completely right, but if you look at that, all of them should align with each other. Sorry, my drawing is not great, but it looks like even there is a two wavelength difference between them, the crust of one aligns with the crust of the other, and that's why this formula holds here, that uh, an integer multiple of wavelength would of path difference means there is constructive interference. For a destructive interference, it should be completely out of phase. The difference should be pi at the end or multiples of pi. So so that's why they have written 2n plus 1 divided by 2, which will give us half, uh, like an odd number of wavelength. Should I say odd? Yeah. No, sorry, not odd. It will just give us like half of the wavelength at the end. Like it can be 1.5 or 2.5 or 3.5 difference in the path length, and it will always be a destructive interference because trough will always coincide with the crust of the other. Does that make sense? And similarly, if you see this example in here, there's some parts are loud, some are quiet. So what happens is there are two speakers that are generating the waves, and obviously at some point the crust aligns with the crust of the other, and some point the trough of the other aligns with the crust of the other, and that's why we have different part differences. We have the path difference. Because of that, we have the phase difference, and because of that, we get to know if this is a constructive interference or destructive interference. Uh, yeah, I should quickly go through it because I want to go through one question as well. Now, we saw that the slit. We had like an example above which had a slit. Now this is a double slit experiment. So two slit experiment, you can see that you can basically see where there is destructive interference, where there is constructive interference, and it is all because of the path length. We'll go through one example and you'll see how that constitutes to that. Uh, this is just a formula that you should just know. So basically, you don't need to know how to basically derive that. You should know that this formula holds for this, and basically it holds. You can basically prove this formula using trigonometry, but I think in your case you don't need to do it. You should just know the formula. X is the spacing of these fringes. uh, Lambda is the wavelength. Both of the slits would have the same wavelength of light going through them. D is basically the distance of, I think, yeah, it's the distance of the screen from the slit where you are actually looking at the interference happening. And A is, I think, the spacing between, yeah, so A is the spacing between the slits, and uh, this X is basically the distance between the fringes. The fringes means that dark light fringes that you see on the screen. Uh, yeah, so these are the formulas that you can use there. So I think that's about it. You don't need to know how to derive them, but you can, if you are interested in that, that is just trigonometry that you have to uh, go through, and you can easily, uh, I would not say easily, but you can derive this formula. Um, Diffraction grating. So yeah, I'll just quickly have a look at this as well. So diffraction grating, it's something like it's also like how it happens in double, like in the slit experiment. Uh, but with a diffraction grating, you have multiple slits, so you have like uh, sharper bands or sharper fringes that you can see on the screen. So and the other thing that you should know is that uh, they so wherever you have bright fringes, they are said to be at an order. So the one in the middle is called zero order, then first on both of the sides, then second, then third. And yeah, so pretty much these are just the formulas that you should know, and that is the only theory that is important. I am just gonna stop here and try to go through one question that I have. I think I have something open. Yeah. So I have written down all the questions that are in all of the boards. I'll just share them with you separately because I know that uh, you guys have different boards. So I'm just going to share them with you for your practice. And obviously, to go through it completely in a proper way, it will take 3 lessons just to finish waves. It can even take 4 if you just go through it slowly. Um, so question 4 shows an arrangement used to investigate double slit interference using microwaves. Figure 5 shows the view from the above. Okay, so there's a microwave transmitter, then there are these slits you can see made out of metal sheets. And because of this is a microwave transmitter, so I'm assuming the wavelengths would be longer. That's why they would need to have bigger slits. So as we saw before. So okay. So yeah, the top view is shown here as well. What happens is what they say. Let's see. The microwaves from the transmitter are polarized, so they are already polarized. These waves are detected by the aerial in the microwave receiver. The aerial is a vertical metal rod, so it's a vertical metal rod, as you can see. The receiver is moved along the dotted line, so it's moved along this dotted line A to E. As it moved, as it is moved, maximum and minimum signals are detected. Maximum signals are first detected at points B and C. The next, so okay, the maximum signals are detected at point B and C. The next maximum signal is detected at D. So they have like noted down where they see the maximum signal, which also tells me that this should basically be the bright fringes, which means that B should be, if we just go to the book, B should be the one that is zero order, and then we have first order, and then second order. So B is zero order, C is first order, and D is second order. Okay. Figure 5 shows the next maximum. Okay. Figure 5 shows the distance between each of the two slits S1 and S2, and the microwave receiver when the aerial is in position D. S1D is, so they have calculated the distance from S1 to D, and S2 to D, they have calculated the distance. Uh, Now the question is, explain why the signal strength falls to a minimum between B and C and between C and D. So it's a 3 marks question. So if I just go like that, I'll just say that there is destructive interference and that's it. So but obviously you have to go step by step because it's a 3 marks question. So do you guys know how would you answer this? Can anybody answer this?
Would you say that between B and C and D,
Hmm.
there's destructive interference because the waves become out of phase? So basically, it's almost like saying the peak of one wave and the trough of one wave meet. So
Yeah.
Mhm.
That completely makes sense. But yeah, that is correct. But so just try to go step by step. So the first step is that there is some path difference. So that is what we also gone through the book. In the book, it says, it talks about path difference. Uh, Path difference. So I think you will start from path difference. They'll say that there is a path difference between the two when it is between B and C and D. There is a path difference between S1 and the distance from S1 to that point on the screen and distance from S2 to that point on the screen. So there's a path difference between the two waves. Because of that path difference, there is destructive interference, as you said that there is the crust. The I think first thing should be to say that there is a path difference between the two, because of how much the distance is from the slits to that point. The next thing is, because of that path difference, the two waves are out of phase, because they also talked about phase in the textbook. So part difference, then you talk about the phase, and then you say hence there is destructive interference, and that's why you see a very uh, like the signal strength is very low at those points. So that would mark as a complete answer. Let me just see as well. So they also, yeah, so they talk about the path difference for the two waves, which gives rise to the phase difference, and then you say that hence there's destructive interference. So because it's 3 markers, so you have to like go step by step, and it's not every time, but when it says three, so you have to make three like factual statements. Not every time, but if you can, you have to. So does that make sense? All right. Then determine the frequency of the microwaves that are transmitted. So to calculate the frequency, now all the formulas that we have seen so far, uh, uh, all the formulas that we went through so far, I just I just remember two formulas where I actually saw frequency. So V is equal to F lambda, and the other one was other one was the same, so it's F over 1 over period. So we have to come up to this formula somehow, because that is what everything points to. There is no other way to come to frequency. Now, to come to this point, If they have not told us the speed, we just take the speed which is in vacuum, that should be 3 times 10 to the power 8 meter per second. The only thing else that is not known in the formula is wavelength. So we need to somehow calculate the wavelength in order to solve this question. So determine the frequency of the microwaves that are transmitted. So what are the things that we know? So the only thing that we know is these path lengths, and these path lengths to the point D, where there is a constructive interference, right? So now the other thing that I think I did not go through, yeah, you see, in the middle, when you have a slit experiment, there is no path difference at all. Okay, so that's why there's constructive interference. Then there comes a point where there is a path difference that has like because of like lambda by 2, so you don't see any signal, or there's destructive interference. Then this point that comes after that, basically uh, which is basically first order. This was zero order, this is first order. At first order, uh, at first order you have a path difference of lambda. So as you keep on going, the difference becomes for the yeah, for the for the first order it's lambda, the path difference. That's why you have constructive interference. For the second order, the difference should be 2 lambda, because it's still a constructive interference, and the difference path difference should also always be n lambda. So it should be 2 lambda. So now if I go back to this is where there is constructive interference, right? B, because and it's what is it called? It's n equal to 0, right? It's a zero order. Yeah, it's zero order. So zero order, then so this is zero order. This is C is first order, then D is second order. So what should be the path difference for the two at D? Can anybody tell me?
Is it 0.056?
Did you? Oh yeah, sorry. Let me just write it down. Uh,
Oh, I did between S1 and
yeah,
S2.
yeah. So what is the path difference that you got?
0.056.
Not
And then
not-
because it said that it's basically the path difference divided by 2, so I divided that by 2.
So
To get 0.028.
so why did you divide it by 2? I did not quite understand. Why did you have to divide it by 2?
Because it it just do you multiply it by 2?
Oh, oh, sorry. So okay, I understand what you are saying. Where is it? So not so you actually divided by 2 and then you got 0 0.056, 0.056, right?
No, I just subtracted them and then I got 0.056.
Okay, all right. And then you divided by 2. So what do you get when you divide it by 2?
0.028. And then because frequencies wave speed over
Yeah,
wavelength,
yeah.
you just use the
Yeah,
speed of light.
yeah. So basically, this is the part difference that you got. Uh, and then because it's second order here, first order and second order, the part difference is 2 lambda. So uh, basically 0.056 is actually equal to 2 lambda, right? The part difference is 2 lambda. It should be this. second. Yeah. Yeah. So it must be equal to 2 lambda, and then you divide it by 2, so you have actually got lambda, and then you can use this formula to calculate lambda, which is v over f, and velocity is 3 times 10 to the power 8 divided by 0.028. How much did you get? The
I got
I have done it wrong. So yeah, f is equal to v over lambda. Yeah, sorry, what did you get?
I got 1.07
Point
times
two.
10 to the 10, or like 1.1 times 10 to the 10.
Yeah, 1
Oh
point.
no, 1.07.
Yeah, okay. All right. And this is in hertz. Okay. Let me see if we have got it right. We got the same answer, right? 1.3. Yeah. Yeah. So we've got the same answer. Yeah. Yes, we have got
Why
got.
is it to the 9 though? Can we still write the answer that we got? Would it be correct?
Yeah, it should be correct. Does it say anything here? 1.07. 1.07 times 10 to the power 9 should be correct. Yeah. And I think that's how we write in scientific notation. Anyway, I am not sure why they had to write it like that. But one thing, so let me just let me just have a look again here. So we had three significant figures. So we have to keep the number 3, uh, and they have not told us anything else. So uh, did you say 1.07? Yeah, 1.07 times 10 to the power 10 should be all right. Should be all right. Doesn't say here, but it should be all right. Okay. Yeah. So that is correct. All right. Okay. Then we have the intensity of the waves passing through each slit is the same. The intensity of the wave passing through each slit is the same. Explain why the minimum intensity between C and D is not zero. So obviously the minimum intensity would be between C and D where there is destructive interference, right? Or between B and C where there is destructive interference. Now the question is, explain why the minimum intensity between C and D is not zero. So can you think of anything why it is not zero between C and D? Because if there is destructive interference, uh, ideally they are generated by the same transmitter as well. There should be uh, there should be destructive interference and there should be zero signal. But they say that it's not zero. So do you have like justification for it? Can you think of anything? No? So, so I think now when they have said that it's not zero, we have come to the real world now. So even if you have like a ripple tank, for example, or even if you throw a stone in water, obviously the amplitude of the wave closest to the stone is greater than to the amplitude of the wave when it has traveled like a meter or two. So you can see that the wave, it does not like come up in a way that it does when where you have actually thrown the stone. So basically at that point the amplitude is greater, so which tells us when energy is traveling, when the wave is traveling, energy is traveling and it keeps on becoming less and less, and that's why the amplitude does not remain the same. So basically when light travels from S1 and S2, to what points are they saying between C and D? Between C and D, obviously S1 would have traveled a longer distance compared to S2. So S1, there is a possibility that its amplitude would have decreased by then. And when there is destructive interference between C and D, now now the crust and trough align to each other, but the amplitude of both of them is not equal to each other. That is why we have some signal there and it's not zero. Does that make sense?
So is it because the wave loses energy over time?
Yeah, exactly. It loses energy over time. That's the reason. Let me see if this is intensity. Yeah, so intensity decreases with distance. One wave travels further than the other. Amplitude intensities of the wave at minimum points are not equal. So yeah, again, because this was uh, yeah, it was a 2 marks question. So yeah, but we have to try to write at least those many factual statements, and but our answer is correct. All right. The last question here is the vertical aerial is placed at position B and is rotated slowly through 90 degree until it lies along the direction A. So that vertical aerial, which is actually measuring the intensity. Uh, this is what it says. Yeah, right. The receivers. Yeah, the receiver. It's measuring the intensity of like if it is what kind of interference is happening. So they're saying that now they start to rotate it. So when they have started to rotate it, it's a question of polarization. So I'll come back to that. So slowly through 90 degree until it lies along the direction AE. Now it's completely vertical to the position from where the wave is coming. State and explain the effect on the signal strength as it is rotated. It's exactly this problem that we went through here. Yeah, this one. So as both of them are vertical, the filters, if you start to rotate the other one, obviously it is at an angle now, and it will have two components. Like you can split it into two components if you consider it a vector. So one of them will still be vertical component, and as you keep on moving it and make it horizontal, its vertical component will keep on decreasing. And because of that, less and less light will go through it until when it becomes completely horizontal and vertical component is zero, no light passes through it. Same is the case here as well. When you keep on rotating it, the vertical component of because it's polarized light that is coming from here. So it's a polarized light that is coming from the transmitter. If you keep on rotating it, if you keep on rotating it like that, uh, at this position, maximum light will pass through it. But when you keep on rotating it, now not all of the light will pass through it as it is at an angle from the incoming light. So some of it will pass through it based on the angle for it as per how you split it into components, and hence when it completely goes to 90 degree, then no light will pass through it and nothing will be detected. uh, let's see how they have explained it. The signal decreases, becomes zero. The waves transmitted are polarized. Obviously, you have to mention that the waves that are coming are they are not mixed waves. If they were mixed wave, then some of it will still pass through it, and it's not going to show any signs of decaying of light. Zero when detector at 90 degree to be transmitting aerial direction of polarization. Yeah, so it will be at 90 degree. It will be uh, there will be zero transmission because it is completely opposite in direction to how the light is polarized and it is coming towards it. Does that make sense?
Yeah.
All right, good. So yeah, so I think I was only able to go through this much in this lesson. Obviously, it will require at least 2 more lessons to go completely through it. I have written down all of the questions that are related to this in the exams for all of the boards. I'll just shortly send them to you, whatever is relevant to you. I hope You have learned something. Is there any question that you have related to what we studied today?
Can you go over that question again? The one about finding the frequency, 4.1.
Oh, yeah, sure.
Oh,
Sure.
4.2, 4.2.
4.2, yeah. So, determine the frequency of the microwaves that are transmitted. So, how I do any question is I just want to know how I can reach to frequency. So I think if the question is even hard, it just becomes a bit easier if you do it that way. So yeah. So I just write the formulas which have frequency in it. So that is V equals F lambda, and the other one is F is equal to 1 over T. I don't think we are gonna use this. If I come to V is equal to F lambda, velocity, if it's not given, we know it's air. We usually take it 3 times 10 to the power 8. But there is still one unknown here, which is lambda. To calculate lambda, what can you do? So what are the things that are known to you? What is known to you for the point, like for example D? The only things that are known to you are the distance from S1 to D and the distance from S2 to D. Now this tells me, if I go back to the book, I don't know if I'm at the right position. Maybe it was below that. Yeah. So that is path difference basically that we are calculating. So path difference is whatever the difference in the distance of the wave that has traveled. So I calculate the path difference from here. So it's 0.667 for the wave that is coming from S2, and 0.723 meters is the distance covered by the wave coming from S1. When I take the difference, that is the path difference. So we have successfully calculated the path difference. Now the second thing I know about a double slit experiment is that the point that is just in front of them is where you have the bright spot or the bright fringe. That is known as zero order. Then the next bright spot on either direction is second order, then third order. So the path difference, this is just a fact. The path difference at B is zero, because at B both of them cover the same distance. At point C, the path difference is for first order, the path difference is equal to just one wavelength long. So whatever is the wavelength of this, it would be just one lambda equal, the path difference would just be equal to one lambda. For D, it's second order. So the path difference between the two must be equal to 2 lambda. So when you calculate 0.723 minus 0.667, which is the path difference, uh, yeah, S1 minus S2, which is 0.056 meters. That should be equal to 2 lambda, because we are talking about D, which is second order. So 0.056 is actually equal to 2 lambda. If it is equal to 2 lambda, just take 2 on the other side or divide both the sides by 2, and you will get 0.028 meters. And 0.028 meters is actually lambda for you. So you just put this 0.028 into this equation, V is equal to F lambda. Everything is known except F, and you will eventually get the value of frequency, which is 1.07 times 10 to the power 10 hertz. Does that make sense, Jishant?
Yeah, thank you.
No worries. Are there any other questions related to this? If not,
Got an A level paper, an AS paper.
sorry, this question is in AS paper.
Yeah.
Yeah. This is in AS paper. I think it's 2017. Yeah, 2017 AQA. I have written down all the questions. I'll just send you shortly. If not today, I'll just send you all of the questions related to this topic tomorrow. All right. Okay. So if there's no other thing, then I'll just leave. So I hope that you gained something today. I hope to see you soon again. So take care. Bye bye.
Thank you.
No worries. Bye.
Thanks, bye.